In Lesson 36, Paul introduced us to servo motors. Our assignment in Lesson 36 is to control a servo motor with a potentiometer. Turn the pot left, the servo turns left. Turn the pot right, the servo turns right. Servo motors do not rotate continuously. Rather, they rotate to a particular position and stop. Servo motors have three electrical connections: power, ground, and control. The Pico W is able to power the servo motor included in the Sunfounder kit, but Paul was very clear that other larger motors should be powered from a separate power supply. Remember to make the Pico and the power supply grounds common if you try this. The servo motor position is controlled by a train of pulses applied to the control line. The servo expects the control pulses to have a period of 20 milliseconds. We're going to be sending these pulses from the Pico W using PWM, which is set up in terms of frequency, not period. So we calculate the frequency of the required 20 millisecond pulse train as 1 over 20 milliseconds, which is equal to 1 over 0.02 seconds, or 50 hertz. During each 20 millisecond period, the pulse train will be on for some time and off for the remainder of the time. The percentage of on time controls the position of the servo. If the pulse train is on for 2.5% of the period, or 0.5 milliseconds, the servo will move to 0 degrees. If the pulse train is on for 12.5% of the period, or 2.5 milliseconds, the servo will move to 180 degrees. The Pico W controls PWM outputs by adjusting their duty cycles. The maximum duty cycle of a Pico W PWM output is 65,535. So to position a servo at 0 degrees, we require a PWM duty cycle representing the 2.5% on time, or the integer value of 2.5% of 65,535, which is 1638. To position a servo at 180 degrees, we require a PWM duty cycle representing the 12.5% on time, or the integer value of 12.5% of 65,535, which is 8191. The servo does respond linearly as duty cycles change between 1638 and 8191. The left side of the potentiometer will be connected to the ground rail, and the right side will be connected to the 3.3 volt rail. Not the 5 volt, 3.3 volt. The wiper is attached to analog to digital converter 0. When the pot is turned completely to the left, the analog digital converter will sense 0 volts and report that as an ADC value of 0. When the pot is turned completely to the right, the ADC will sense 3.3 volts and report that as an ADC value of 65,535. A straight line equation will convert those ADC values representing pot position into servo duty cycles, which determine the servo position. Here we see a graph that shows our analog digital converter value as the independent variable. It will range from 0 when the pot is fully left to 65,535 when the pot is fully right. The dependent variable in this case is servo duty cycle, and it will range from 1638 up to 8191, from 2.5% of 65,535 to 12.5% of 65,535. We can create a straight line equation to calculate intermediate values. We'll call our X1, Y1 pair 0 and 1638, and our X2, Y2 pair 65,535 and 8191. Using those 2 points, we can calculate the slope of the line as shown on the chart. Once we have the slope, we can calculate the y-intercept for this line. Obviously, it's 1638. So if we read the potentiometer value in a while true loop, convert the pot value to a duty cycle using this equation, and send the duty cycle to the servo, we should be in business. Here's the code. As usual, we start with some imports. We import machine because we're going to be using PWM, and time because we will want to call the sleep function. Next, we declare the pins we'll be using, 18 for the servo control line and 26 for reading the value of the pot. Once we declare our pins, we can create our servo and ADC objects and set the frequency of the servo object to 50 Hertz, representing the 20 millisecond period that the servo motor requires. As an alternative to hard-coding the parameters for our pot value to duty cycle equation, we can let the Pico do it. We'll specify the max and min expected values for pot readings and servo pulse width. This lets us calculate the max and min duty cycles that we'll be sending to the servo motor. The Pico uses those numbers to calculate the M and B values for our equation. We summarize our calculations in the shell. Finally, in the while true loop, we read the value of the pot position, convert the pot position to a duty cycle, send that duty cycle to the servo, and then sleep briefly to lighten the load on the servo and do it all over again. And here's how it looks. Channel 1 of the oscilloscope is connected to pin 18 of the Pico, the servo control line. Channel 2 is connected to pin 26, the analog to digital converter input reading the pot wiper voltage. At this point, the voltage into the ADC is 0 volts. This drives the pulse width of the control signal to 0.5 milliseconds, which is 2.5% of the 20 millisecond period. A 2.5% pulse drives the servo horn to 0 degrees. As the pot knob is rotated to the right, the voltage on the ADC increases, as you can see in channel 2, making the pulse width of the servo control signal longer. The servo horn moves accordingly. When the pot reaches the right-hand end of travel, the wiper voltage will be 3.3 volts. Once we reach 3.3 volts, we can confirm that the width of the control pulse is 2.5 milliseconds, which is 12.5% of a 20 millisecond period, just what we needed to drive the horn to 180 degrees. As we turn the pot back to the left, the input to the ADC drops back towards 0, and the servo horn returns to 0 degrees. We can verify the pulse width has returned to 0.5 milliseconds. And that's it. We've controlled the position of a servo with a pot. Well, that's it for this assignment. Any and all comments are welcome. Don't forget to like or dislike the video before you go. And feel free to subscribe. Don't forget the notification bell. We'll talk to you next time.